Well, where we were last time, just to review, we did the decoders, and then we talked about the multiplexers, and we talked about the demultiplexers. And the demultiplexers, kind of like a decoder, except instead of just activating one of these things, like on or off, it relays some input, whether it's on or off. That's the key difference. And then I was saying the programmable logic arrays. And what's neat about a programmable logic array is you can create any truth table that's like coherent, and you can make it if you follow the pattern of a programmable logic array. However, I will warn you, it's like a very brute force strategy to create the logic, where it might be a lot better or simpler to do it another way. But a programmable logic array is like a brute force strategy where you're guaranteed to get whatever you want. And they're handy. But there's always like engineering trade-offs, right? Where, okay, this brute force strategy works and all, but it's at the cost of a lot more, so. Anyways, programmable logic arrays are general purpose. It's an idea of a design for implementing really any Boolean functionality we want. We can map any input to any desired output. They're effectively decoders where the single decoded output signal may activate multiple final outputs. All right? They consist of two main parts, a collection of AND gates called the AND array, which acts as the decoder, followed by a collection of OR gates called an OR array, which activates an output when specific decoded signals are high. Okay? The number of AND gates depends on the number of inputs. So given n inputs, there will be a total of 2 to the n AND gates, just like decoders. We really do have like one big decoder, all right, where a signal will activate whenever specific bit patterns arise. And then the number of OR gates depends on the number of desired outputs. Imagine it's like here's the idea. Before I get to it, here's the general idea. We have a decoder. Let me get a better one. Okay, here's our decoder, okay? And we have, let's say, 4 outputs. Okay? So, okay, let's create a truth table. A, B. All right? And we have 4 outputs. 0, 1, 2, 3. You can all see this pretty reasonably well? Yeah? How about over there? Can you see that? You can? Cool. So 0, 0, 0, 1, 1, 0, 1, 1. So let's say I want like the output to be like 1, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0. That's what I want it to be. Whenever the input is 0, 0, I want the outputs to be 0, 1, 2, 3. Okay? And then, so really what I have to now do is, okay, we've got the decoder part that will like activate one of these signals. Okay? And really, the signal that we get is going to correspond to like the row. And then we basically brute force will make those outputs high when we see that row. That's what we're getting at here. So how can I map this one signal to multiple outputs? Well, that's easy. I can branch a signal to 4 outputs, right? 0, 1, 2, 3. This is separated, right? Okay, great. So now I want, well, really, actually, I only want 0, 1. There. I want this to be mapped directly to those things. But then, like, when I see this signal here, I want this one to be mapped here. But can we combine outputs like that? No. We use an OR gate. Okay, so we would actually turn that into an OR. Okay? And we want it to output to that one too. Okay? And then this one we want it to map there. But again, we would have to combine those with an OR. And then finally, this last one we want to go here, and we combine that with an OR. Meaning, all I really have to do is turn this into a fancy OR gate. right? And there as well. You get the idea. It's a decoder followed by, well, combining whatever outputs we want for each, of the signals coming from the decoder. That's the idea. It's a straightforward idea, but it's a very brute force idea. So here's an example where we only have 3 outputs. Okay, great. We can do this. It doesn't matter. 3 outputs. So if I want to make a PLA for this, okay, what do we have here? 2 PLAs, 2 input PLA with some output to make connection of inputs and outputs. Yeah, so this is showing like, okay, I've added the step of like, well, imagine I've created the decoder here. That's what this is. All right? So how do I then map this to that? Well, that's pretty easy. We just combine the ORs. That's the idea. So from the table, output 0 is high. When the 0 is, whatever. So here's the idea. Here's the programmable logic array for that design. Now, you might be wondering, why am I showing these lines go on? No real reason other than I think it helps with some like visual clarity. Because the point is that like these lines, like if they weren't there, it would be kind of hard to keep track of like, wait, where's going where, where's going where? When you see lines like this, it's kind of just showing you that, how do I explain it? I don't know, I find it's easier to follow the pattern of like what's happening here. This AND gate outputs to this line. And then everything that connects to this line is to that AND gate. Like it's easier to follow it visually, I find. It's not to suggest that these go on forever. No, I mean, they're not, if they're used elsewhere, fine, but probably not. So it's not to suggest that they go on forever. It's just there for the visual clarity. Is that clear what I mean? I think it helps separate things. And you might say, why don't I have it here? Well, I think this one's a little bit more straightforward because this one gets a little kind of like crazy. What do I want connected where? Well, it depends. Like that one, it's all over the place. I could have more outputs. It's easy to add more outputs to this. But that's the idea. This part here, you should be able to recognize that's a decoder, right? 0, 0. 0, 1, or sorry, 1, 0, 0, 1. It depends on which way you think about it, but yeah, that's the decoder part. And then the decoder goes into like this array of the OR gates. That's the idea. And like I was saying, with this design, you can implement any truth table design you want. And this is big, all right? Because this idea is going to come up several times for the computational system that we're going to design, the computer that we're going to design. However, a programmable logic array is effectively a dictionary, okay? You map a unique input, the key, to some desired output, whatever you want it to be. It's like a lookup table, okay? We can think of programmable logic arrays like this. And we're going to think of these things like this because this we can scale this forever. But if I said make a 7-input PLA with 20 outputs, do you want to make that? Do you want to start implementing? No. So we immediately go, okay, but let's just, okay, here's another one, right? As you can see, like, it's not complicated to make, but it's certainly a pain, right? You can look at this and be like, oh, whew. Now, by the way, you could actually, within digital, you can actually, I'm just showing you right now for the sake of it. Perfect, I have it open still. Analysis, synthesis. You can actually design a truth table and it'll generate it for you, which is pretty cool. But we're going to skip that step. So the point I'm making with this, right? Like, look at this. Look at this thing. It's huge, right? And this is how many input? 3 input. It's only 3. And this grows exponentially, right? 4, 16. 5, 32. That's going to get big real fast. And our computational system is going to, it's going to get kind of big. So if you want to start designing something like this, we like to abstract it out and be like, it's a lookup table. All right? That's the idea. And we call them lookup tables, or LUTs, okay? Now, there's no specific symbol for this idea within digital circuitry. And whenever you have a component where there's no specific symbol, you just kind of add it, maybe you label it, a box with a LUT. It's a lookup table, all right? You're going to see a lot of abstraction that looks just like a box like that, all right? So this lookup table, I can go and manipulate this lookup table to give me whatever I want. Do I show you? Yeah. Let me make sure I didn't miss anything here. Okay, maps the decoded signal through the OR gates, the basic design. So this design, again, I want to be clear. If I were to tell you right now, if on a test I said make a 4-input programmable logic array that does this, it should be easy for you to do it. The hardest part would just be making sure you're not making clerical errors. All right? Because it's just a decoder, followed by you map each decoded signal to the output you want high, and they might need to be connected through AND gates to avoid short circuits. Okay? It's very simple, but painful. And that's why we say, okay, just a lookup table. Okay, one may have realized it's like a map, dictionary, lookup table. In fact, within digital programmable logic arrays are called lookup tables. Below is a figure. There we go. Okay, lookup tables are an abstract idea, and as such, the physical implementation is often not important. We know this functionality we want, so how does it, yeah. So in practice, these lookup tables could be programmable logic arrays constructed with AND arrays and OR arrays, or they could be implemented with a form of memory mapping. We're going to learn about memory very soon. But at the end of the day, like RAM. If I say ROM, do you know what that means? Really? You don't know? What does RAM mean? Random access memory. Okay, please tell me more than one person knew that. Yeah. Okay, good. But no one knows what ROM means? Random optimized memory? No. Read-only memory. It's fine. It's fine. It's fine. It's you shouldn't feel bad about yourself if you don't know, but maybe a little bit. Yeah. Because they don't remember CD-ROM. They don't remember CD-ROM. Fair enough, right? You know what CD-ROMs are? Some people actually said no. All right. You know DVDs? It's what we had before those bad boys. Who here's? Please tell me you know what a DVD is. Okay, good. Just checking. So it was like, okay, I guess Blu-rays are though, right? But okay. They are, and they're they're a niche technology because streaming became so big, right? That they kind of. Anyways, ROM, read-only memory. So random access memory. We're going to talk about memory in more detail, but you can envision memory as a nice analog as like a list. All right, think of a Python list. All right. Where you've got, and we like to pretend it goes on forever, but it doesn't. But a list has indices, right? Okay? And with random access memory, what I can say is I've got some data stored at index, but if it's memory, usually we would say like address. But index, address, and we kind of we mix and match these words often. I could say go to memory address 3 and put the number 14 in there. All right. And go to memory address 1 and put the letter B in there. Okay, cool. Right? And then later I can be like, what did I put in memory address 3? I can go investigate what's there, and then I can modify what's there with random access memory. It's nice. It's volatile. It can change. We're going to build RAM within digital. It's going to be fine. It's great. There's also read-only memory, which is a memory which you can write to, but it's not designed for frequent writes. It's designed for reads. When you program it, obviously you're writing to it, but it's not really designed to be changed once it's set. And what's nice about ROM too is like on your computer with RAM, although you use something called DRAM? Well, there's DRAM, I might be getting it wrong, but this is not important. The RAM you have, like when you power off your computer, the information in RAM is, it's gone, right? That's fine. With ROM, the idea is it's persistent, okay? But that really does depend on how things are implemented. We're not going to get too much into it. But at the end of the day, you can treat ROM as a lookup table. Address, value. Going to there, input bit pattern is like the address, and the output is what's stored at that address. It's an abstract idea. How it's implemented, whether it's a programmable logic array, read-only memory, whatever, it's a lookup table, okay? It's a more abstract idea that is separate from its underlying implementation, all right? That's the point I'm making here. Any questions about that? All right. So functional completeness. As seen with programmable logic arrays, any Boolean logic function can be implemented systematically. In other words, any function can be physically created with a configuration of AND gates and OR gates and NOT gates, right? Because the decoder has a series of NOT gates too, right? Inside of it. So this means that the set AND or NOT is functionally complete. You can do whatever you want. But as we have seen in the labs and in your assignment, raise your hand if you're not done the assignment. Wow. Halfway? Okay. All right.
Digital card takes like 10 minutes.
Man, I really made it way too easy for you. All right. Don't worry, I won't make that mistake next time. It depends. Oh, you're hedging now. Okay. All right. So whatever. Although only other gates exist, they're not necessary. It's not necessary that we have exclusive OR because we can make exclusive OR with these gates. Who here made? Remember how I said a moment ago how like these programmable logic arrays are like they're like brute force though, right? How many of you made your exclusive OR with a programmable logic array? No, but you could. Right? So how did you, point being like, there's might be other ways to go about doing it. So nevertheless, they may make configurations of circuit easier. So even though AND or NOT are all you really need, we might like exclusive OR gates because, it's just easier to write an exclusive OR gate. It's a more abstract idea. However, review De Morgan's laws. These two things here. These show that with OR and NOT, I can create the functionality of AND. Right? Why? Well, look at this first one here, right? If I not A or not B, I get not A and B. And if I not that, I get A and B. That's just AND. Right? Because I knotted a knot, and that's, Right? So with only OR and NOT, I can create AND. And similarly, with only AND NOT, I can create OR. That's what I'm showing here. Right? So here's like that, right? Cool? However, as we have clearly seen from labs and the assignment, you can go even lower. If we give ourselves only NOR or NAND, we can build everything. So the minimal set to do everything in a computer is NAND or NOR. That's all you need. To me, I want to make sure you gain an appreciation for that. All you actually need is the fact that we have true and false, and A, B, and let's do like NOR. Oh no, yeah. Let's do NAND. I like NAND better. That's all you need. This, the fact that this maps to this, this maps to this, this maps to this, this maps to this. That's all you actually need to make all of the computers that we ever use. It's wild. That's it. You need 3 things. A true-false state, a 0-1, some binary state, and this operation. That's it. And I know we kind of joked about it before. If you're like, well, NAND, that's really not an AND. Forget the name. I don't need to name this. I don't care what I call it. That's the mapping I care about. With that mapping, I can do whatever I want. In fact, because for engineering reasons, it's easier to fabricate one type of gate, that's what I literally do. I make a crap ton of NAND gates and configure them, and that's how these computers work. It's crazy. I don't know. I hope you get what I mean. That right there got us to the moon. All right, so anyways. Any questions about any of that rant right there? I don't know. It wasn't very much, though. I don't even know if it was that high. Someone look it up real quick. How much RAM was on the spaceship that went to the moon? It's all, to me, that's where, when you are working in such a limited, constrained,
4 kilobytes of RAM.
4 kilobytes, there you go. Bytes or bits?
Bytes.
Okay, 4 kilobytes, okay.
Which one did the Apollo 11 computer have? I guess that's
How much do you have on your computer? 16 gigs at the least? That's a lot more. That's orders of magnitude more. But that's all you need, right? It's crazy. It's always fun to me working in such constrained spaces, like minimal RAM, minimal instruction set. Because that's where like it forces you to be creative. That's where like you see like a form of artistic expression, for lack of a better term. What were you going to say?
I just had a question about the programmable logic array.
Yes.
So it's programmable in a sense that you can make it output whatever you want, but not like programmable, like you can go back in and change it around?
I mean, depending on how you physically implemented it, if I've got like a series of gates on a breadboard, I can go and change out the gates if I really wanted. But programmable in the sense that like once I create it, like I can program it. And don't think programming as like typing code. As like, you can think of programming as like, who knows what like never mind. Like I design it, I program these arrays to do whatever I want. That's what it means. If I've like built this onto like an integrated circuit, yeah, I'm probably not going to be able to go change it out very easily, right? But if I've got like a series of gates on a breadboard, yeah, I can swap them out however I want. Usually all you need to swap out is like this configuration, because the decoder's the decoder. Yeah. Other questions? All right, what do we got next? Memory. Oh, speak of the devil. All right, so until now, all the circuits we've made, there's no like, their functionality never depended on a state, some information that existed from before, like no state, all right? there was no use of stored information. But obviously on the computers we use, it's important to have information stored, right? Like, what was the result of the last operation I did? Or like, what was that picture I had stored on my computer? Like, you want to store data. So yeah, obviously. So memory can be used to store data, such as the value of a variable, or some instructions, like a program. When you have RAM on your computer, your RAM, whenever you load up a program, your RAM is filled with data and instructions. They share the same address space. In the computer systems we use, you could design a computer system where they have separate address spaces, but we don't typically use those. And there's pros and cons. But anyways, instructions and data. Although really, instructions, just data. But you know, we like to talk about these things as separate things. Even though they really are, instructions are it's just data. All right, bits, bytes, and data. All right. Before getting into the details of memory, I want to make sure we're clear on encoded and decoded information. I've hit this point several times already this semester. We're to the end of the third week, right? So, pardon? Right? It's the third week, right? Yeah. All values within a typical computer are encoded as some binary pattern, right? So if I have 011000001, what is that data? You don't really know. I mean, you know that like it's an encoding. 011000001 probably means something. I mean, maybe it doesn't. But it probably means something. But what does it mean? You don't know unless you are told how to decode it. So the binary pattern is an encoding that can have different meaning depending on what it's encoding. And literally, if you were to open up your computer and be like, what is this? That pattern, if you look at it in terms of like, well, what's its binary, like what's its integer value? Well, it's 97 base 10. It's 97. Great. But it could also mean lowercase a. The pattern for 97 and lowercase a it's exactly the same. 01100, I can't see that. 0110001 means 97, and it also means a. But I couldn't tell you what it really means unless I told you what's the encoding. All right? To be very clear, that's what I mean here. So the binary patterns have different meaning. It could also encode the color blue. It could also be a pattern to control circuitry within your CPU to perform something like addition. You don't know until I tell you, or until you know somehow what is it encoding. The encoding and the decoding are separate things. You need some function to map one to the other. Is that clear? All right. No. Okay, the word data is used to refer to, so this is like traditionally speaking, I'm going to abuse this. Everybody does. But if we want to be really pedantic, the word data is used to refer to raw values and symbols that have no like intrinsic meaning, while the word information really does have a separate meaning. You might mean like data, information, what's the difference? Well, here's the difference. Data is like the raw values, symbols, whatever, but information refers to like the meaning of the data in some context. There actually is a difference in what these words mean. Now, how many of you have been aware of this difference? One person that might be lying. You're just trying to impress me. You know? Well, there you go. 2 people in this room knew. Wow. Right? Point being, how important is it that we differentiate here? In our lives, we've gotten this far. It's not, I'm going to mix this up. We are all going to mix this up. But, you know, it's important to be aware that these words have separate meaning for the sake of, you know, that has meaning for us here, right? 0100111. Oh, that means A, right? All right, for example, the number 3 alone is data, but the number 3 can be information if it's referring to some quantity of ducks swimming in a pool or something. So 0110001 is data, but what it means is information. Okay? I'm going to mix this up. You're going to mix this up. Whatever. It's fine. Not too much of a big deal. But, you know, there is a differentiation here. A single bit is the most basic unit of data in a typical computing. In a typical computing system, I don't know what I mean there, but a typical computing apparently, as already discussed, a bit is a single binary digit. Okay? It can have one of two values, a 0 or a 1, as opposed to a decimal digit, which can take on the value 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Right? So binary one, that's a bit. A bit is represented within computers as a single signal. These bit signals can take on two possible states. We often refer to this as 0 or a 1. Really, there are no zeros and ones in these computers. It's either the signal is there or not, on or off, high voltage, low voltage, but we think of them as on or off. Okay? This means that with one single bit, I can represent two unique values. We know that. I can have two unique states. I know, especially because how I introduced binary, when I introduced binary, I introduced it such that we were referring to integers, to numbers, right? So you're like, oh yeah, it could take on the value of 0 or 1. Yes, but you're already like assigning meaning to the states, where really it's just a pattern. It's just one of two states. We like to assign the value, okay, it's off, so it's 0. And then what? There. Here's another bit. Now it's 1, right? 0, 1. The value is 0 and the value 1. Great, but we've already assigned meaning. The fact that it's on or off doesn't necessarily mean it must be a 0 or a 1. In terms of like, when I say mean the integer 0 or the integer 1, it's just two states. Okay? Cool? As more bits and signals get added, more possible combinations of states, more unique values can be created. So in like base 2, with n bits, a total of 2 to the n unique values can be represented. So with 2 bits, I can have 4 states. Again, we can look at this and be like, oh, that's 0, 1, 2, 3. Yes, but I'm assigning the labels 0, 1, 2, 3. Really, it's just these 4 unique patterns that I presented in this order. All right? I'm emphasizing this to really hit home the differentiation between an encoding and meaning, the data versus information. They are separate. And having this in your mind is going to be very important as we go forward. Here's the 4 states, right? Off, 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 on, off, on. Right? Cool. Any questions so far? A byte is a group of 8 bits. The reason why it's 8 is, it's not arbitrary, but it's nearly arbitrary, and it's for historical reasons and practical reasons as well. We're not going to worry about covering why it's 8, but it is. All right? It has to do with like letters and the old computers that they designed, and then they went with 8. And from that reason, we're with 8. I've probably said this to y'all before. I always thought it would be really cool to have a course on like the weird trivia of computers. And like, why is a byte 8 bits, right? Stuff like that, I always thought it'd be kind of neat to learn why, but it's not important right now. Why is Vim ridiculous? Well, there's a reason for that. And it has to do with the old keyboards, but whatever. All right, so here is a byte, 2 to the 8. If I have 8 bits, I can represent 2 to the power of 8 unique things. I can have 2 to the power 8 unique patterns. So that means a total of 256 unique values. It could represent the numbers between 0 and 255, or it could represent letters and other characters and whatnot. Cool? Cool. So here's 011000001. 0, 1, 1, 0, 0, 0, 0, 1, assuming we go in that direction. All right? And above is an example of a byte encoding some data. Assuming the top signal is the least significant bit, this pattern is 0, 1, 1, 0, 0, 0, 0, 1, like I said. But it has no meaning without its context. Really, that pattern is just some data. It's not really any information. It doesn't tell us anything. When I say least significant bit, I mean this one. Most significant bit, I mean that one. Same with like most significant digit, right? I have the number 752. Which one of these numbers is the most significant? Well, it's the 7. That's the big one, right? Yeah, that's what I mean. Random access, RAN. Random access memory provides a way to store data for later use. There are several different broad types of memory within a computer, and they all serve the same general purpose. For our course now, we're going to focus on two different types of memory. Random access memory. It stores data and instructions the computer is using, and registers. That's like storing the data and instructions like the CPU is actively like processing. All right? For this topic, we're going to be talking a little bit about RAM. So we know what a byte is. Now we're talking about RAM. So why and how are these things related? Okay. Address space and addressability. I'm throwing like definitions at you, but I'm going to show you what they mean, and I think it's going to be kind of easy to understand. So in a typical computer, RAM stores data the computer is using along with instructions of the program being run. And like I said, technically instructions are data, but whatever. So RAM is commonly made up of a number of memory locations, like I was talking about with a list. Think of a list that's really long where you can index these things. Each of these locations has a unique identifier with a memory address. That's like the index. The number of uniquely identifiable locations is referred to the address space. So, if I had, how can I word this? If I had 2 bits to address memory, I can have a total of 4 memory addresses. That's the address space. Each memory location stores some amount of data or instruction, but the same thing. And the amount of data stored in each location is the memory's addressability. These things are separate though, and it might be kind of hard to kind of wrap your head around it, but we'll see. So usually RAM is byte addressable. In the computer systems that we use today, RAM is typically byte addressable, meaning I have a unique identifier that can pinpoint every byte, every grouping of 8 bits, okay? That doesn't mean, like, for example, like if you're using computers, like if you're programming in Java, and you access an integer might take up a few, like if you're storing an int, someone do me a favor and like in Java, how many bytes is an int? 4, that's what I thought. 32 bits, okay? 32-bit integers, okay? Meaning we can uniquely identify like 2 billion or so integers, right? Or 4 billion, whatever it is. 2 to the power of, what's 2 to the power of 32? Someone type that in real quick. It's probably like 4 billion, right? 4 billion and a half, something like that. 4.29 billion, okay? So that's why, who here took 162 with me last semester? You might not remember this, but, wait, 162 last year. That's what I meant to say. You might not remember this, but do you remember in the first assignment how to store the population, we couldn't use integers. We had to use longs. double is floating point, double precision. We had to use longs. And the reason is because, well, we might have populations that are over what 32 bits can represent. Now, we could have gotten around it on our current planet, in the current state of things, by using an unsigned integer, but those don't exist in Java. It's a whole thing. We're going to learn about that later. Point being, whatever, we have 4 bytes. Okay, so our RAM, our computers are byte addressable. Your computer has the ability to be like D, like A, B, C, D, E. All of these things represent 1 byte. Okay, there's 8 zeros and 1s in here. Okay, some combination of them. Your computer has the ability to say, like, give me the one here, give me that one. It can, but depending on the data, your computer knows, if I want to decode this, there's a little bit more going on. It goes like, okay, well, an integer is actually 4. So if I want the integer stored at index, or at memory address 0011, it's actually like 1, 2, 3, 4. It actually takes up this chunk, right? And in certain like, if you were to play around with C++, for example, you could, and you start playing around with pointers, if you add 1 to an integer pointer, it actually adds 4. I'm pretty sure that's how it works. And you'd be like, why is it adding 4? Well, it's actually adding like how much room, like how much room you would have to go to get to the next integer. It's neat, right? Okay, cool. So like think if you had an integer array of size 4, of 4 integers. Well, you would need like 1, 2, 3, 4. That's one integer. 1, 2, 3, 4. That's another integer. 1, 2, 3, 4. But at the end of the day, your computer is still byte addressable. Each one of these memory locations stores a byte, and I can get it. Yeah. All right. So the above figure provides a high-level visualization of RAM. In this figure, there are 16 unique memory locations. How do I know it's 16? Well, there's 4 bits. So with 4 bits, I can uniquely specify 16 things. And we usually refer to these addresses based on their integer value. So address 0 through address 15. Because 0000 means 0. And 1111 means 15. And you're like, wait, he said 16. 15? And 0 is also a thing, right? So don't forget about 0. 1 through 15 and 0. In this figure, there are 16 unique locations. Each memory address contains some data represented here as some character. Here, I'm A, B, C. It's just some arbitrary value. It's not, oh, the byte that represents the letter A. No, it's just whatever. I just picked a symbol. If one, for example, asked, what is stored at memory address 3? The answer would be D. 0, 1, 2, 3. There we go. Cool. If you're like, yeah, this is just like a list. Nailed it. Absolutely. Good job. However, like memory addresses, the data being stored is some pattern of zeros and ones. Okay? Cool. All right. Any questions so far? Okay, so imagine we're going to start with this like ideal, like what do we want? And then we're going to like build it. Okay, so let's try to like think. Okay, well, how would we want to do this? Well, imagine I've got some magic construction, some magic way to store 1 bit. 1 bit memory. Okay, I'm representing it as a box from digital. All right, this box doesn't exist as this within digital, but let's pretend we have something like this. I can store 1 bit like that. So if I want to store more than 1 bit, well, I can just get more of them, right? If 1 is 1 bit, I can put 4 together and have 4 bits. Somehow. How we configure these things, we'll figure out later. But the idea is if 1 can store 1 bit, 4 can store 4 bits. If 1 now wants the ability to store several groups of 4 bits, well, I could just stack those groupings of 4 bits. If I say, give me this one, well, I get these 4 bits. If I say, give me this one, I get these 4 bits, right? We could pretend maybe these are the, this is the address space, Okay? Do I want 0, 0, 0, 1, 1, 0, or 1, 1? And the addressability here would be 4 bits, half a byte. Anyone know what the general word for a half a byte is? A nibble. That's not a joke. That's what it is. Anyways. Why? Because it's not a whole byte. It's a nibble. Right? Anyways. Come on, that's funny. You're allowed to laugh at that. So, address space would be like, sorry, how much we have here, and addressability is, well, how much can I get out of here? This would be like half byte, 4-bit addressable. Okay? Only 4 spaces. Cool. So consider a 4x4 block of RAM. Consider this. 4 bits per memory address and 4 memory addresses. So how many bits can I how many bits can I actually store here? Well, 16, right? 4 by 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I can store 16 unique bits, which is neat. For this RAM to be useful, though, we need a way to be able to put data into it and get data from it. So I need a way to be like, okay, go to this row of 4 bits and put information in it, or retrieve information from it. We need some way to be able to do that. I would need 2 address lines to specify which of the rows I have, right? In fact, doesn't that sound kind of like a decoder? If I had 2 address lines, I could activate one of these 4 rows, right? With a decoder. That's perfect. I would need 4 lines coming in, right? So maybe it's actually more like a demultiplexer. If I've got signals coming, maybe not. I don't know. We'll figure out. I'd have 4 lines coming in to be able to put data into RAM, right? So I specify one of these rows with like a decoder or something. But then I have lines going to each of these things to be able to like, well, what value do I want to store in each of these things? So I would have 4 lines going to these. Well, all of them, really. And 4 lines coming out, right? Because I want to be able to get data out as well. 4 data lines required to input the data into the 4 things. And I'd have 4 lines coming out to get information out. Now, fortunately, decoders and multiplexers, we already talked about decoders and multiplexers. And so they provide a way for us to do exactly this. This is like some configuration we could have. I've got my decoder to activate one of these lines, right? Now you might be like, is it more important that like the decoder is what's going? No, I'm just like showing you with some consistency how like, okay, this would like activate this row. Okay, the fact that the lines, the fact that it's going into the second row, second input on this button, and that's not really actually important. I'm just showing how it's connected. And this would be the data lines, right? So maybe the data line could be trying to put the data in all of these rows for each bit along, but only the one that gets activated would actually like read that data from that line. Okay? So let's say this row is giving me a 1. There's a 1 trying to be put into each of these boxes, but only the address line that I care about would actually like accept it. Okay? It's turning its ear on. And then similarly to output, they're all outputting, but this is a multiplexer. They're all outputting, but which of these lines, well, depending on the address line, which one do I actually want to output? We'll start back up here on Tuesday. We'll start with this picture here. But this is the idea.